Hello everyone, my name is Takero, and I am a chemistry tutor. I can tutor AP Chemistry as well as college level general chemistry and organic chemistry. I can also tutor AP Calculus. I am a recent graduate of Stanford University, where I received a Bachelor of Science in Chemical Engineering. With the coursework heavy in math and chemistry, calculus and chemistry have been two subjects that I've been very engaged in. I've been fortunate enough to have many wonderful instructors in chemistry, and this has pushed me to excel in chemistry and has also motivated me to make chemistry as understandable and enjoyable as possible for other students. I have more than 6 years of tutoring experience, where I started tutoring math and science in high school and later served as a chemistry tutor in Stanford's Center for Teaching and Learning. I've also been a teaching assistant at Stanford for one of their chemical engineering courses. Okay, so now we're going to do an example of a synthesis in organic chemistry. And synthesis problems are really common because they test your cumulative knowledge on organic reactions, and they also make sure that you know how to utilize different reactions in a synthetic pathway. So they're very common questions. They tend to be worth a lot of points, so it's definitely worth going through an example of it. And what is a synthesis problem? Well, basically, you're given a starting material or starting materials, which I'll call SM here. And then you're also given a final product or a target product, which I'll call P. And basically, once you're given those molecules, you want to provide a sequence of reagents that'll transform the starting materials into the target product. So let's work through an example. Let's say we're given these starting materials. So those are your starting materials and your final product. And you want to provide a series of reagents that'll go from these starting materials here to this final molecule here. So the first thing I like to do is look for similarities between your starting materials and your product. And it's not that obvious in this case because you have two chains and you have like a ring molecule as a product. But if you look closely, you can see that this here in blue is kind of similar to this here in the starting material. So there's some similarity, and you can also notice that there's a nitrogen in both one of your starting materials and in the product. So you have this here in red connected to some carbons, and you also have this nitrogen here connected to some carbons. So I like to do this as a first step just because it kind of orients me to see where the pieces might fit in throughout the synthesis. And the next thing I like to do for synthesis problems is to count the number of carbons. And this might sound really trivial, but it's actually pretty valuable because it can tell you whether you need to have any reagents that add or remove carbons and whatnot. So if we count the number of carbons in the product, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. And if we count the carbons in our starting materials, we have 1, 2, 3, 4, 5, 6, 7, 8. So we also have 8 carbons total in our two starting materials. So this suggests that all the carbons in a product are likely from just the starting materials, so you don't have to add or remove any carbons throughout your synthesis. Okay, so now that we have done our initial bookkeeping, let's look at how we can approach this problem. So the way I like to approach synthesis problems is to think both forwards and backwards, and we call that a forward synthesis and a retrosynthesis. In a forward synthesis, you're basically asking yourself, what can I turn the molecule of interest into? So let's say you have a molecule A, you can turn that into many different things. And you basically want to see if any of these reactions could possibly help convert your starting materials into something that's more similar to your product. And in a retrosynthesis, you're basically asking the question, what molecule could turn into my molecule of interest? So let's say you want to get to B, you're basically thinking of as many different possible molecules and reagents that can achieve this conversion. And ultimately, you're going to do this forward synthesis and retrosynthesis as many times or as few times as you want to until they converge so that you get a cohesive synthetic pathway. So if we apply this thinking to this problem here, let's start with doing a retrosynthesis on our final product P. So retrosynthesis. So we know we have this product here, and we ask ourselves, what could this molecule have come from? And upon first inspection, you might think to yourself that, oh, I have this ring here, I have an amine group here, so maybe it's an intramolecular SN2. So in that case, you would draw this retrosynthetic arrow saying, okay, maybe I have an NH2 here and a good leaving group, the Br. And this is plausible because the N here can attack this to give you your final product. So here's one possibility. Another possible molecule is an imine, because as you hopefully know from your reactions, an imine can be reduced using sodium borohydride into an amine. So in that case, that would look like and your reagent would be sodium borohydride with the appropriate workup. Okay, so we've identified two possible pathways that will hopefully get you from your starting materials to your final product. So let's look into these two cases and see which one's more feasible. If we look at the second case of the imine, we can recognize that an imine is formed from a carbonyl and an amine. So this can be broken into something like this. H2. And if we compare these two molecules to our starting materials, we notice that one of our starting materials, the one on the bottom here, this one has a carbonyl just like we do over here. And in fact, they actually look pretty similar, because again, you have this region here, which looks just like this region here. Whereas in the other case, you don't have any carbonyls here. So this should suggest to us that perhaps it is the second case that is the more feasible pathway for the synthesis. So we can cross out this one and go with this one. Okay, now we're one step closer to getting our starting materials to our final product, or our target product. So this might be a good time to do a forward synthesis. And as a reminder, our starting materials are this and this one. And our objective basically is to go from these starting materials to this intermediate molecule right there. So let's compare the starting materials to this intermediate molecule. We see that there is a similarity in the blue region with this carbonyl. And also we see that the nitrogen and the carbons it's attached to might also have something in common here. However, we need to connect these two pieces together so that we get this linkage right here. So how can we do that? Well, hopefully you remember a reaction using a strong base where you can deprotonate the alpha carbon, the alpha proton right here, and have that attack a good leaving group, like here. So a good way to do that is using a strong base like LDA. And when you do that, you'll get a molecule that looks like this. And I'll also draw that out as this so that it looks a bit more similar to what we want. Hopefully you can notice the similarities between this one and this one. The only difference right now is that we have an NH2 group here and an N3 group, and we'll take care of that. So now we're getting closer. The next step is to convert this azide N3 to the amine, the NH2 here. And there's a pretty easy way to do that. You can simply hydrogenate it. So I'll do hydrogen palladium catalyst. And that should give me NH2 here. And we see that this is exactly the molecule we want. And essentially, we've completed our synthesis. But because we decompose this problem into so many steps, it's always good to just put things together. So, putting it together. Through a combination of forward synthesis and retrosynthesis, we've come up with a series of reagents that can get us from our starting materials, these two, into final product. And now we're just going to combine all the steps that we've brainstormed for a full synthetic pathway. We first begin with this and this. And starting with this, we first react it with a strong base, LDA, and then we put in this. And this would get us to our first intermediate compound. Next, we want to reduce this azide to an NH2, so we can hydrogenate it. And in order to make our amine using this NH2 and carbonyl group, we can add some catalytic acid. So a catalytic amount of, say, HCl will give you your amine. And this is the same as these are the same. And finally, we reduce the amine with sodium borohydride and make sure to do our acid and base workup. And we get our target product. So, boom. We get our full synthesis from our starting materials to chains to our final product, which is a ring. Although they might look very different, using all the reactions you've learned from organic chemistry, you should be able to come up with something like this using the strategies like thinking forwards and backwards. And if you're able to do this for many different problems, then you should find success in your organic chemistry exams. I hope you found the video informative. If you're struggling with the concept in chemistry or want to brush up before a test, I would love to help. I hope to meet you soon. Thanks for watching.